So it's a great pleasure to introduce the Associate Professor André Beck, that is going to deliver a lecture for us today on epistemic uncertainties and their role in optimal design of engineering system. So just a quick overview about Professor Beck. Let me just get here that there are so many things to say. He graduated from Universidade Federal do Rio Grande do Sul in 1986, and then he obtained a master's degree in mechanical engineering at Universidade Federal de Santa Catarina in 1998. And then he went overseas to Australia and he obtained his PhD degree in University of Newcastle. Since then, he has been working at University of São Paulo, São Carlos, the campus of São Carlos, and mostly working with structural reliability, computational mechanics, stochastic analysis, and uncertainty quantification. And also, I would say that now a little bit of also risk analysis. So he is the member of the editorial board of the Journal of the Brazilian Society of Mechanical Science and Engineering, and also of the ABCM Journal of Risk and Uncertainty in Engineering System and Structural Safety. Also, he's a member of this CNPq Civil Engineering Advisory Committee. His term is from 21 to 24. André Beck, I've known him since he arrived at USP, and it's one of the persons that I know that most published in Brazil, and that's one of the most recognized internationally that I know here in the country. So, André, again, it's a great pleasure to have you here, and I'm sure we will enjoy very much your presentation. I know bits and bits of this presentation, but I'm very excited to understand a little better and to learn a little more with you. Thank you very much for accepting our invitation, and the floor is all yours now.
Okay, Luis, thank you for the nice introduction, and thank you for the invitation to speak at this special session of the conference. My talk today will be about the epistemic uncertainties and their role in optimal design of engineering systems. I have to start acknowledging the participation of two students, and unfortunately I forgot to include the slide here. Lucas Araújo, who is in the audience, and also Lucas da Rosa Ribeiro, who helped producing the results that I'm presenting here. To start with the motivation, just to see here. Motivation to this work is the optimal design of redundant structural systems with objective consideration of progressive failure. So because of my background in civil engineering, this is the problem that I was studying when I run into these issues that I'm going to talk about today. But as you can see that the title is broader, it talks about engineering systems in general. I'm quite sure that you guys who are working in mechanical engineering, electrical engineering, will find something useful here to take to the problems that you address. So I will first talk a few words about design optimization under uncertainties, how we assemble the different problems in structural engineering. And here we see a relationship between the uncertainties that affect an engineering system, the structural behavior or the mechanical behavior of that system, which is related somehow to the cost of manufacture, the cost of assembling, building, constructing that system. The primary effect of the uncertainties is the possibility of failure, a possibility that the system will not behave as expected, and a secondary consequence when we multiply this probability of failure by the consequences of failure, we have the expected cost of failure, which we can understand also as risk, given the definition of risk as a probability times a measure of the consequences. When we talk about deterministic design optimization, normally we are looking for a D star value, which will minimize the manufacturing costs or the volume of the structure, subject to some deterministic failure criteria involving, for instance, an admissible stress or partial safety factors. When we broaden the scope of our problem, we find the formulation of reliability-based design optimization, where we are looking for a D star which minimizes the same manufacturing costs or the same volume, but now the deterministic failure criteria are replaced by admissible failure criteria in terms of admissible failure probabilities, either for each failure mode of the system or the failure probability of the system itself. And when we broaden a little bit more the scope of the problem, we have what I have been calling risk optimization, or also optimization of costs over the life cycle of a structure, where we now will look for D star or for the optimum safety factors, or even the optimal failure probability, which will minimize the total expected costs of the structure. So during this presentation, I will be talking about RBDO, reliability-based design optimization, and about risk optimization. One important thing to keep in mind when we talk about risk optimization is that we need to quantify the expected consequences of failure. So when we address a given structure and we want to find an optimal structure which is either isostatic or hyperstatic, we need to differentiate the costs of a direct collapse for an isostatic system and the cost of progressive collapse for hyperstatic systems. So we use different cost multipliers to differentiate the consequences of failure of an individual bar of a hyperstatic system and of the individual bar of an isostatic system. Okay? And for the hyperstatic system that does not suffer progressive collapse, then a single bar failure can be understood as equivalent to a service failure, where we only pay for the replacement of that failure member. So we don't have a collapse of the structure. We only have to replace one member. Now, before we try to solve this problem, we need to make a small classification of the uncertainties that might be involved in any structural problem or system engineering problem in general. We make a distinction between what we call physical uncertainty and epistemic uncertainty. The physical uncertainty is that related to natural phenomena that we need to deal with, such as wind, waves, earthquakes, droughts, floods, strength of soils and materials. And the epistemic uncertainty, on the other hand, is related to limited knowledge, model limitations, phenomenological uncertainty, social matters, financial markets, human error, terrorist attacks, unanticipated loading, this type of things. Epistemic uncertainty is mostly subjective and largely unpredictable. Physical uncertainty is what we call objective uncertainty, mostly predictable. Physical uncertainty is mostly unreducible, whereas epistemic uncertainty is in theory reducible if we investigate more about the problem, if we learn more about the variables that we need to deal with. The physical uncertainties are what we call well-behaved or Gaussian, and the epistemic uncertainty might be wild and sometimes require power law to describe the probabilities involved. And we could also make a reference here to a famous sentence by Donald Rumsfeld, who was the Secretary of Defense of the United States at the time of the Gulf War. Physical uncertainty are what we call known unknowns, but the epistemic uncertainty enters into this classification of unknown unknowns. So the physical uncertainty are the things that we know we don't know, but we need to deal with. And epistemic uncertainty, unknown unknowns. Physical uncertainty is mostly modeled using probability theory. So here we use random variables, random processes, random fields to characterize this type of uncertainty. However, the epistemic uncertainty is mostly modeled using possibilistic theory, which includes intervals, nested intervals, or what we call fuzzy variables, fuzzy or imprecise probabilities, which is a combination of fuzzy intervals with probabilities, and so on. And when we think about the way we solve the uncertainty propagation in our problems, normally we use what is called a black box. So this black box here may represent the physical problem that we are going to address, like the finite element model of our structure, the fluid mechanics problem, whatever. If we have probability in the input, we have probability in the output. So this requires uncertainty propagation in terms of probability through our system. Now, if we have fuzzy probabilities in the input, we will have fuzzy probabilities in the output. And because of this combination of fuzzy uncertainty with probabilistic uncertainty, we obtain nested loops of uncertainty quantification. So if I'm going to talk about optimization, within the optimization loop, I will have a loop to handle the fuzzy uncertainty, another internal loop to handle the probabilities, and in there is my black box. So this means that I will have to be solving this finite element model millions of times in order to handle the fuzzy and the probability parts of the uncertainty. Now, this is the proposition that I make here. For the physical uncertainty, we use probability theory. For the epistemic uncertainty, we may use possibilistic theory to handle subjective uncertainties arising from ignorance, vagueness, and subjective judgment. However, we have several other types of uncertainty that are not well modeled using possibilistic theory. And this is, for instance, gross errors in design and manufacturing, unaccounted load cases or failure modes, human errors, operational abuse, and so on. When we look at the history of structural failures, we see that many historical failures can be justified because of these type of uncertainties here. And so the proposal that I'm making here in this presentation and in the corresponding papers that have been publishing recently is simply to add a term which I call the latent failure probability. So I will use probability theory to arrive at a nominal failure probability which will reflect all the physical uncertainty that I can quantify, but I will add a constant term, and I will interpret that this constant term is imposed on my system because of these things here. Okay, and I might not have a very precise way of knowing the value of this latent failure probability, but as I will show you in the sequence, I don't actually need to know the precise value for this probability. I only need to know its order of magnitude, because this will have a significant importance in our optimization problem. Now, the very good thing about it is that if we don't have fuzzy variables in our problem, if we don't have this type of uncertainty listed above, then I will have probability coming inside my black box. I will simply have probability coming out, and I will add a probability term. So I did not change the nature of the uncertainty that I have here in this inner box. And this means that comparing to the case before, I have removed one level of nested analysis, which significantly simplifies the uncertainty propagation within the optimization problem. Okay? So the idea is that the reliability of structural systems depends on non-structural factors, or factors that are not object of design, like the workmanship operational abuse, strength degradation eventually, failure due to unanticipated loads, terrorist attacks, and so on. And in order to take care of these uncertainties, we will add a latent failure probability. During the presentation, I will also mention or talk about a latent reliability, which is simply a transformation, actually a reliability index, okay, which is simply a well-known transformation that relates probabilities with the reliability index that we use here to obtain this latent reliability. And in this illustration, I'm trying to develop the concept showing that our structural analysis, our finite element model, will be handling the objective aleatory uncertainty in the loads, model parameters, material strengths, and so on. So this will be handled via, for instance, Monte Carlo simulation. So this means that we will need to be solving this finite element model hundreds of thousands of times. And we will always involve this structural analysis in a risk analysis where we will address the mixed uncertainties, like the threats that the structure is subject to, the use of the structure, the material quality, the workmanship, human errors, and so on. And typically, a risk analysis like this uses failure trees and event trees to yield the normal and abnormal loading scenarios. Okay, sometimes loading scenarios that have very high intensity and very small probability of occurrence. And some of these loading scenarios are of epistemic origin, as we are going to see during the presentation. So the idea is that out of this risk analysis, we obtain the loading scenarios that we need to consider in our structure, but we also obtain some measure of the order of magnitude of what would be the latent failure probability. Now I will start with a very simple application, and this problem is actually where all of these discussions start. And it's very simple because we want to understand what is going on. So we take the simplest possible parallel system formed by two bars, bars 1 and 2, which are sharing a given load P, either in an active-passive way, which is represented here in the left, or in a standby or passive way, which is represented in the right. Okay, so in the right, we see that element number 2 is only mobilized after failure of element number 1. So what is coming out here is valid both for this type of system and for this type of system. And because it's very simple, we can obtain analytical formulations for everything. So first, we start with the physical uncertainty, and we assume that our material has a random strength. Different could be two different materials. There is even a coefficient of correlation between the strength of the materials in the two bars. And also, I consider here an elastic perfectly plastic model with this variable eta equals 1, or a fragile material with eta equals 0. So I can easily switch between fragile and ductile material behaviors. Also, because this structure has at the beginning two bars, I will assume that it is subject to two load impulses, each one with a given uncertainty, represented here as a normal distribution with a mean μp, deviation sigma p, and both with the same magnitude. And also, I assume that after failure of one of the bars, I may have a dynamic load amplification, which is represented by this factor Fi, dynamic load amplification factor. Of course, I have to consider that the two bars share the load, and this sharing depends on the stiffness of each element. And because I want to address the optimal design of this bar, and because I want to ask, is the second bar necessary? This is the main question that I'm trying to ask here. Does this system need to be redundant? And when does it need to be redundant? Under what conditions? So I make an independent design of each bar using these factors lambda 1 and lambda 2. So lambda 1 is the design factor for bar 1, lambda 2 is the design factor for bar 2. The problem will tell me if the structure needs to be redundant or not. So our problem has a vector of random variables formed by the two material strengths and the intensity of the two load pulses, two deterministic design parameters, lambda 1 and lambda 2, and three problem parameters, one characterizing material behavior, one characterizing correlation between the material strengths, and one characterizing the load amplification that might occur in this problem. The limit states for the individual failure of each bar, because they will be written as stated here, and the failure probability for each bar will be evaluated from this classical reliability integral. So this is the joint probability density of all the problem random variables, and I will need to integrate this over the failure domain for each limit state function. And because I am modeling these uncertainties, uncertain parameters as a normal or Gaussian distributed, that means that I can obtain an exact solution by calculating this reliability index, which is the expected value of the limit state function divided by the square root of the variance. And this is related to the failure probability by way of this same equation here, where this is the cumulative standard Gaussian distribution. Okay. Now, of course, because I'm handling with the system here, I need to make the failure tree for the system. So when I apply the first load, I have different events that may happen here. This first event means no failure of bar 1 intersection with no failure of bar 2. So nothing happens to my system in the first load application. In this dotted square here, we have the union, meaning the failure of bar 1 or the failure of bar 2. And that means that could be failure of bar 1 only, failure of bar 2 only, or an intersection where both bars fail simultaneously. If both bars fail simultaneously, we have a direct collapse of the system. If only one bar fails, then at the second load application, we have to update the strength of the system and we calculate the probability that the second bar fails, given that the first bar has failed already. If the second bar fails, we have progressive collapse. If only one bar fails in both load applications, we call this a service failure. And if nothing happens, we have no consequences. So we will use consequence factors which are different for the service failure, for the direct collapse, and for the progressive collapse. The primary failure events can be written as this. So you can see here, very simple. This is the area of each element times the strength of each material minus the load applied. Okay, so we can obtain all of this in closed form. This here are the conditional failure events. So the probability that bar 2 fails given that the bar 1 has failed will be given by this expression, where we see the residual strength of bar 1 if ni is different from 0. Here is the load dynamic load amplification, and so this is also comes in analytical form. This is the joint failure event now. Both bars failing simultaneously, and this is the reliability index for the joint failure event. The system reliability will be the probability of failure due to bar 1 minus the probability of an intersection times the probability of failure of bar 2 given failure of bar 1, and so on. And here is the probability of simultaneous failure of both bars. The objective function for this problem in the RBDO formulation only involves the cost of the structural materials. And we write our optimization problems as find D star, which is the optimal safety, partial safety factors, which minimize the cost of structural materials, given a given reliability target. We will specify. when we quantify the expected consequences of failure, then the objective function is the total expected cost, where we can see here the cost factor for a service failure, which meaning the failure of a single bar, the cost of progressive collapse, and the cost of a direct collapse, times the probability of all the events involved. For the risk optimization formulation, the optimization problem is to find lambda 1, lambda 2, which minimizes this total expected costs, which includes the expected consequences of failure. Now, these are the results that we obtained for RBDO in terms of partial safety factor 1 and partial safety factor 2. For different values of the problem parameters, we have here a correlation between material strengths 0 or 0.9, and a load amplification factor of 1 or 1.3 for a fragile material with eta equals 0. And we see straight lines for different target reliability indexes. So target reliability 1, 3, and 5. What these straight lines are telling me is that in terms of RBDO, a solution where the partial factor lambda 1 is 0 and lambda 2 is 2.2 is equivalent to a solution where lambda 2 is 0 and lambda 1 is 2.2. And this is equivalent to a solution where both lambdas are equal 1 or roughly 1. So the problem is telling me that redundancy is may not be necessary. But we know that redundancy is good. So something is still missing, right? We know that our structural systems are many times redundant. And what is missing? Precisely the concept of latent failure probability. So in this particular problem, in order to have an objective modeling of the impact of this latent failure probability, I assume, okay, I want to find the optimal cross-section areas of my elements, but I also need to consider that the connections between the elements and the structure, they might fail. And they are not objective of this optimization. Of course, somebody could say, okay, maybe you have to include the connections also in your optimization problem. But then I would say, yes, but also remember that if this is part of a structure, any of these two bars might be impacted by a vehicle, which has not been considered, or it might be subject to a terrorist act, or any other non-anticipated loading condition that will lead to a failure probability of each element. So here, I consider this as the uncertainty of the connection, but this could be any source of uncertainty that makes me lose one of the elements, any of the elements, and which is not due to load P. So conceptually, this is well put here. And because I don't want to make my problem too complex, I assume the same value for the latent failure probability for both bars. Okay, so we have only one parameter to look for its effect in the problem. Now, of course, when we insert here the probability that each element fails at the first load application, then our failure tree increases significantly. This first part now are all the possible events that characterize the failure of the bar, but not because of application of load P. This would be because the connection is broken, okay, or because there was a manufacturing problem in the connection, and so on. This is the system reliability now also becomes a little bit more complex. The objective function also grows. And now we look at the results when we consider the latent failure probability. To the left, I have the same results as before, with latent failure probability equals 0. And to the right, I have included a latent failure probability PL equals 10 to the minus 3 which corresponds to a target reliability index of 3.09. It's written here in red. So 3.09. And now we see, this is the latent failure, the latent reliability, or this is the reliability imposed on the system by these other sources of uncertainty. Now, if I impose as a target reliability to my system anything below this latent reliability, the optimal responses are still on a straight line here, okay, showing that isostatic and hyperstatic solutions are equivalent. But if I put a target reliability which is slightly higher than this latent failure probability, then the problem is telling me that the only way to make my structural system more reliable than this latent reliability is by making it redundant. So the solution with lambda equals 0 here doesn't exist anymore. And now these are redundant solutions with 2 bars. These plots are obtained for the fragile material for different values of correlation strength between materials of different impact factors. So we see that none of this has much relevance. The main parameter here telling me if my system needs to be redundant or not is the latent failure probability. If I change the material to a ductile material, I get very similar results, almost a straight line here for RBDO, going to 0, meaning that isostatic systems and hyperstatic systems are equivalent. But once I insert the latent failure probability, the problem tells me that the only way of making my system more reliable than this latent value is by making it redundant. Now, these are the results for the risk-based optimization. And for the risk-based optimization, we see here the level curves of the objective function. So we still see some straight lines here showing that for the majority of this problem, there is still some equivalence between lambda 1 and lambda 2. But one characteristic of the risk-based optimization problem is that the optimal safety of the system is one of the products of the optimization. So when I insert a latent failure probability, I don't know if it is above or below the optimal reliability that will come out as a solution to this problem. Okay, so I use a value which is below and a value which is above. A value which is below and a value which is above the optimal reliability. And what we see here is that there is still some tendency for a linear behavior, but we see that along this line here, there is a minimum, which is a redundant system. For dynamic load distribution 1 is the plots above. For if I have an impact factor of 1.3, I already get 2 different solutions here, all assembled along this line. So we see that we have a strong gradient towards the line, but we have a very small gradient along the line. And when we have a higher, a latent probability, which is much higher, which makes a greater impact in our solution, then we clearly have here a redundant solution as our point of global minimum. So again, the latent reliability is the main factor controlling the optimal solutions for these problems. These results are for fragile material, very similar results for the ductile material. Again, latent failure probability being the main factor to control the optimal solutions. Now I go to a second application, and Luis, please control my time. Okay, I have some flexibility here to stop in time for questions. So the second application does not change too much from the first, but it is like an optimal topology of a simple truss like this. It's a 6-bar truss with a static degree of redundancy of 1. A load applied to this node, and we are looking for the optimal cross-section areas of the bars of this truss. So the RBDO formulation for this problem is, given a value for the latent failure probability, we want to find the optimal cross-section area of the elements, which minimizes the total, which minimizes the manufacturing cost or the cost of materials for these bars, subject to a target reliability and some lateral constraints on the cross-section areas. For the risk-based formulation, again, for a given PL, we will look for D star, which minimizes the total expected costs, subject to lateral constraints only, where the total expected cost includes the cost of structural materials, plus the cost of hyperstatic failure, cost of a progressive failure, and cost of a direct failure for an isostatic structure, with different cost factors used here to differentiate these different configurations. And what we did in this problem is that we run the latent failure probability from a very small value to a very significant value. And here on the left, we have the structural weight of the optimal structures for two values of the target reliability. These are the results for RBDO. Okay, so in red, target reliability is 3. In blue, target reliability is 4. Obviously, the structural weight increases because we want more reliability, we have to put more material. But what is interesting here is that as we increase the latent failure probability from a very small value up to a given point, which we call the redundancy threshold, the optimal results are indifferent to the latent failure probability. Meaning that in this region here, where we are obtaining isostatic topologies as the optimal solution, the impact of the latent failure probability is very small, and this failure probability in this region is only, or is mainly due to the physical uncertainty. Now, if we keep increasing the latent failure probability, we reach a region here where the optimal design starts to change almost in proportion to this latent failure probability. And this is the region where we obtain redundant optimal topologies for RBDO. Okay, so we identify this redundancy threshold where this behavior changes. But the most interesting results are for the risk-based optimization. And here, with the different curves relate to the different consequence multiplier factors. So K here, 10, 20, or 10 are the consequences of a progressive collapse. And K times alpha with alpha 5 and alpha 10 quantifies the consequences of a direct collapse for an isostatic system. So again, we see here that we have a region for very small values of the latent failure probability for which the optimal designs are basically indifferent to the value of latent failure probability, and where the optimal solutions are all isostatic topologies. Like we see here on the left, the minimum 3 bars that we need to sustain that load P over there. Then we reach what we call here the hyperstatic threshold. And from this point on, the optimal solutions will start to depend on the latent failure probability. Please note that in this plot, I'm plotting the system reliability index and not the structural weight. Okay, so this is the optimal system reliability. And we see that these solutions here are hyperstatic but not redundant. And in this region here, we have these very thin bars, and the cost factors have been calculated in such a way that I understand that if I have a hyperstatic system, which is non-redundant, if one of these thin bar fails because of the first load application, I have time to evacuate my structure or to cease use of the structure because I had a warning that something is going wrong. So conceptually, we have a warning gives us time to evacuate the structure, and this reduces the consequences of failure. So we pay only, if there is progressive collapse, we pay only for cost multiplier K, okay? Instead of the isostatic structure where we pay for K times alpha as a consequence of failure. As we increase the latent failure probability, the optimal results approaches this curve, which I call beta max 3B. This is the maximum reliability that a 3-bar structure can achieve, considering that each bar is subject to a latent failure probability of this magnitude. Okay, so we see that the 3-bar solution, actually the load mechanism involves 3 bars. The other 3 are here more like a fuse to tell me that something is going wrong with the structure. So the 3-bar solution goes up to a point where we call the redundancy threshold. And from this point on, the solution jumps to a hyperstatic redundant topology with 6 bars, meaning that my latent failure probability now is so large that the only way that I can make my structure more reliable is to give it an alternative load path, which is produced by this 2 triangles. Also, it would be the superposition of this load, of these 3 bars on the left with the 3 bars in the middle. So our optimal structure became redundant, hyperstatic and redundant. And if we keep increasing the latent failure probability, this solution eventually approaches the maximum reliability that a 6-bar structure can have, okay? And of course, if our problem were more complex, if it had a higher static degree, a higher degree of static indeterminacy, then from this point on here, we would jump to 9 bars, 12 bars, and so on. So I think this is a quite interesting concept. And now I come to the third application example, and this is more, that goes more, a little bit more towards a practical engineering problem, which is the progressive collapse of frame buildings under column loss scenarios.
So, you're on time. We have another 10 to 15 minutes. Okay.
Yeah, I should be able to finish in 10 to 15. So the formulation here is a classical formulation where we have to combine the probability of occurrence of different hazards in red, the probability of having local damage like a column loss given the hazard, and the probability of progressive collapse giving local damage and hazard. Okay. So in the formulation of this problem, we are going to be addressing specifically this term in green, which relates to the progressive collapse of the structure, considering that it has suffered a loss of a column due to a given hazard, which for us will be any hazard like a terrorist bombing, like a vehicle impact, or anything like this. I will go very quickly here over the formulation. Okay, so we have a given load combination that we need to use under usual design. This is the combination of the dead load plus the life load. And we have a reduced load combination that we use. This is all given by the American design code. The reduced combination that we use in the exceptional loading scenario. So we remove one of the columns of the building, and we need to check that the building still stands under a reduced value of the life load. Okay. And here in this equation, we introduce the lambda PC. This will be the optimal design factor for the structure under progressive collapse situation. Again, I wrote all the equations in analytical form in order to be able to simplify the solution. Okay, this is the total expected cost for this problem. We have lambda PC representing the cost of construction plus a cost multiplication factor times phi of minus beta. This is the beta under normal loading condition. And this is K times the probability of column loss times the beta in the column loss situation. Okay. And again, we compute this solution by first order, second moment, or first order reliability method. And now we have an example where we have a continuous beam like this. Now these are the bending moments. And we're going to assume that it was subject to removal of an internal column like this one. So we have an increase here in the bending moments, okay? Or we have removed one of the external columns, and again, there is an increase in the bending moments. So very simple problem in order to make the solution analytical. And these now are the total expected costs that we obtain in terms of the design factor lambda PC for different values of the probability of column loss. So if you, when you see here, probability of column loss equals 1, we have this curve, and our optimal design has a design factor around 1.2. 1.2 here representing 20% greater than the design factor recommended in the ISC code. If the probability of column loss equals 0.1, the optimal design is around 1. Okay. If the probability of column loss is very small, the optimal design is 0.6. It is basically telling me 0.6. It's telling me it's not worth doing the strengthening of the structure to withstand the loss of the column. And here I see a region where the objective function became flat. And this means that the optimal solution is almost indifferent, meaning that I can either design this considering progressive collapse or not considering, making only the usual design. So this value here is also a transition in optimal in the optimal solution. Okay, it will become more clear in the sequence. And now I'm going to compare the total expected cost of the usual design, the total expected cost for the progressive colline as recommended in the code. This is with lambda PC equals 1, and the optimal solution in terms of the column loss probability. And remember, what is the column loss probability? It's the probability of losing a column. Now, what controls the probability of losing a column in a given building? The use of the structure. If this is a governmental structure from the United States government, they will assume, yes, the probability is high that some terrorist will want to blow out our building. If this building is located near a busy road full of traffic, then the columns in the outer facade are going to be more likely to be hit by a car or a truck in a traffic accident. So there is a lot of epistemic uncertainty here related to the value of this column loss probability. It will be different for different buildings and different environments. So the idea is that all of this will be taken care of in a risk analysis, and that the value that needs to come to my structural optimization problem is the column loss probability, which is very equivalent to the latent failure probability concept. Okay? So when I compare these total expected costs here, I see that the cost of usual design goes to the sky when the column loss probability increases. On the other hand, the cost of progressive collapse design is smaller when this failure probability is, when this column loss probability is significant, but it becomes more expensive when the threat is insignificant. And when I compare these two curves, I found a value here where the two curves cross each other. And this is telling me in this very point, it is equivalent to make the progressive collapse reinforcement or not. Okay, and you see that my optimal solution is always below here because it's always looking for the optimal design. Okay, but this particular point where the two curves cross is of very relevance to us. And is basically showing us a threshold. I call this the column loss probability threshold. And I'm saying that if the column loss probability is smaller than this threshold value, then I should not be concerned with progressive collapse design. If the column loss probability threshold is above sorry, if the column loss probability is above this threshold, then I should do the progressive collapse. Okay. Now I go to a more realistic problem. This is the design of a regular plane frame, which can be subject to initial damage of different magnitude, meaning with the like a bombing or a car accident, with the removal of 1, 2, or 3 columns. This building is made by NC columns and NS stories. Okay, so it's a regular building. And I assume here, also to make the problem simple, I assume that any column of the building could be removed due to an epistemic, an event of epistemic origin. And so my reinforcement action is I have to reinforce the first 2 floors, all columns and all beams of the first 2 floors, because these are the potential targets for column removal. Okay. And this problem is quite interesting because once I remove the columns here from the middle, the failure can progress in different ways. So I can have a progressive bending collapse where I lose all the floors above the affected area. I can have local crushing of the adjacent columns. And this crushing can progress horizontally, provoking the global pancake collapse, where the whole building will fall flat like a pile of pancakes. And I also can have the crushing of the column affecting beams for n+2 base and turning into bending collapse. And all of this has been introduced into the problem as the system analysis for the propagation of the consequences of failure. Okay, so we use here a design factor for the beams, a design factor lambda c for the columns, and we are going to find, I'm going to skip over all these details. I'm going to look, this is the total expected cost function, where I'm going to look for the optimal safety factors or optimal design factors for the beams, optimal design factors for the columns, where 1 corresponds to the conventional usual design situation as specified in the ASCE codes. Okay, and here I have the cost of construction, which is of course proportional to lambda b and lambda p. And here are the different events that occur in this problem. So this is like local collapse, pancake bending collapse, global pancake collapse. This is for number of removed columns +2. These are all the different consequences of failure if the progressive collapse failure goes on. Okay, I think I'm going to skip over these plots too. And this now the total expected cost function as function of the design factor lambda b for the fixed lambda c. I fix lambda c is at the optimum value here, and we see very similar plot to that one that I obtained for the continuous beam. So for column loss probability equals 1, optimal design is here around 1.2, something 1.3. Okay, if column loss probability is very small, optimal design is here around design factor for the beams around 0.3 or 2, meaning that I should not be reinforcing the beams to withstand the progressive collapse. And in the middle here, for a value of 0.023 for this particular structure, I see again 2 points of local minima telling me that it is equivalent, or there is an equivalent total expected cost if I make the conventional design or if I make the reinforcement considering progressive collapse. Okay. Now this problem becomes very interesting when I look at buildings with different configurations. So a low building, which is 4 stories high by 16 stories wide, or a tall building with same area, which is 16 stories high and 4 stories wide, for base wide. And then I see that this threshold column loss probability that tells me when the reinforcement is cost effective, I see how it changes with the aspect ratio of the building, depending on the internal aspect ratio of the base, with the cost factors that I use to characterize ductile and brittle failures, with the alpha factors that characterize the cost of steel, considering that most of the reinforcement has to do with putting more steel in the reinforced concrete structure. And this is changing with the size of the initial impact area, okay? And I can also look at the optimal design factors, lambda B and lambda C, as function of the local damage probability. So again, we see that for very small local damage probability, the optimal design factors for the beams are significantly lower than 1, meaning it's not worth reinforcing the beams to withstand progressive collapse. Sorry, here I'm comparing not beams and columns. I'm comparing the tall and the low building. Okay. So we see that for the low building, the optimal safety factors are higher. And in this other plot, I am looking at the optimal reliability again for a tall and for a low building in terms of the local damage probability. And here I have the optimal design factors for the beams. See, this is the optimal reliability of the beams, the optimal reliability index of the beams, the optimal reliability index for local crushing of the columns and for global crushing of the columns. So this would be like a systemic failure of the whole building. Of course, the reliability must be much higher. And in this plot, finally, I'm looking at the optimal safety factors or the optimal design factors, lambda B and lambda C. Below are the results for bending. Above are the results for crushing for different aspect ratios of the frames. And there is one quite interesting behavior that we see here. For instance, if I start with a low building, the optimal bending factor is around 0.8, 0.7, and it starts to increase. So I increase the height of the building, and I have to increase the optimal design factor for bending, because the failure consequences of a bending failure, they propagate upwards. Now, on the same time that I am increasing the bending factor, I am decreasing the crushing factor of the columns up to a given point, meaning that I need to compensate this increase in the safety factor for bending with a reduction in the safety factor for crushing. But then at the given point, when my building starts to become too tall, I need to increase the crushing factor again. So what we are seeing here is a competition between the different failure modes of the structure for the strengthening budget, meaning a competition between the bending failure, the local column failure, and the global pancake collapse. And of course, lots of different details here. So with this, I conclude the presentation, where the main concepts that were presented here were the concept of the latent failure probability that we introduce into the problem to take care of the epistemic uncertainties. Also, the identification of these hyperstatic and redundancy thresholds in the optimal topology optimization problem. And here we point out that the latent failure probability concept can be used as a tool to provide minimal redundancy in topology optimization. And finally, we also came with this concept of column loss probability threshold that tells us for a given building if the usual design is more economical, or if progressive collapse design or reinforcement of the structure to withstand progressive collapse is more economical for each structure. So thank you for your attention. And since I run out of most of the time for questions, if you want to have more details, you can find the 3 sets of results that I presented here in those 2 papers and in this paper, plus another one which is under review. So thank you for your attention again.
Thank you very much, Professor Beck. I will open for questions. I think we can afford another 10-15 minutes here. So please, if you have any questions, you can write on the chat, or you can just click on the reactions and raise your hand. I have like the first one is a question. The second one is I just want you to talk a little bit. So the first a question, like when I talk to civil engineers and we think about like mainly trusses, they are always looking to find the term trusses, or as you call the isostatic truss, right? And that's because then they can have defects of manufacturing, they can have temperature variation, they can have support settlement, and there is no additional internal forces to the truss if it's a determined truss, right? I wonder to what extent, like you defend very much the undetermined or the hyperstack truss or structure.
Yeah.
I wonder to what extent we would be able to do like a study to measure the comparison, you know, like for the engineer to know, well, actually, you're actually better off if you design a determined or undetermined truss, because I don't know how to take into account the support settlement, the effect of fabrication, the temperature variation, and all these things that for the engineer it's quite important. So do you have any take on that? And the second one, because it's super short, it's for me, like when you presented pieces of this presentation to me before in the past, like my head just blew just on things to do, like in how much you have opened by finding this topic to research. And I wonder if you can share what are you thinking about the future of this research topic?
Okay, thanks for the second question. That's very interesting. I'm not that sure about the first one because I never thought in this line as isostatic being better to avoid some of the load cases you mentioned. But one of the results that I ran into when I was trying to interpret the results that I was obtaining in these optimization problems that I solved were some studies from the 70s where people were studying system reliability, and it became evident to them without doing the studies that I'm doing here, like with optimization, it became evident to them that if I wanted to avoid gross errors in manufacturing or due to unanticipated load cases, there was no point increasing the design factor or making an isostatic structure stronger. There was no point, because if you put, let's say, lambda equals 2, you make it twice as strong as it needed, but it's an unanticipated load case. It's a load of unknown magnitude that might destroy your member. So the conclusion there was, in order to cope with gross errors, make the structure redundant. And this is exactly the same solution that is coming up here based on a more objective concept, which is introducing this latent failure probability. It is telling us exactly that, okay? Now, as for your second question, I briefly mentioned in my presentation that the history of structural failures is full of collapses that occurred due to epistemic origins, errors in management, errors in manufacturing, even errors in design, and also phenomenological uncertainty, failure modes that were not known at the time. So my objective for the next 2 or 3 years is to try to justify the existence of this latent failure probability, not from its usefulness. I think I try to prove the usefulness of that concept in this presentation and in the papers that I published already, but I'm trying to develop the case for its existence from the historical perspective. Like showing, for instance, look, historically, we have designed bridges with a given the target reliability, but we have observed smaller reliabilities in the actual structures. The difference between what we designed for and what we observed can be completed by this latent failure probability. So I hope to be able to show this for particular structural cases.
Nice. Thank you.
I have a question.
Marco, yeah.
Two questions actually. Can you hear me all right?
Sure. In the meanwhile, let me ask everyone to turn on their cameras so we make a picture here of a screenshot of the talk.
Sure.
For the social,
So,
for the social networks or any other use you can think of. Please go ahead.
Go ahead.
Okay, so thanks for the talk. I work with deterministic linear elasticity, so this is very much out of my comfort zone. But I think you did a great job with walking us through the steps to be able to understand.
Please,
what you're talking
let me
about.
ask Lais to mute her microphone. There's an interference. Lais, please. Thank you. Go ahead, Jose.
Did you hear the first part?
Yes, yes. You were talking about linear
Okay,
analysis, right?
Yeah, so I work with deterministic linear elasticity, which is,
Yeah.
It's a very small box, and you're talking like things about here, but you did a great job to connect these two dots and walk us step by step in order to understand this problem, which is very interesting how to, question our way of thinking about problems in general, right? So if I understood well, we can take a lesson for engineering practice, even if you're not considering uncertainties at all. That if you can identify a certain probability of failure where the redundancy threshold starts, then you can design the structure using only physical uncertainties.
Yes,
right? Because you
for
have
instance.
that constant line there where you need to start having redundancies after that line, right? So the first question is it possible at all to identify that line in terms of failure probabilities so that we can be comfortable with designing structures?
You mean the threshold?
On the realm of, linear elasticity.
You mean the threshold?
Yeah.
I think we should be able to, but of course this is all very new and still being discussed with the special communities. Can you still see my screen here?
Yeah.
Let me reduce this with the images here. So this plot here, when I showed you, I did not mention, but because we know that our structures need to be redundant, and exclude the small comment by Luis Vieira before, okay? My understanding, our structures need to be redundant. My guess is that the latent failure probability that we are coping with is of this order of magnitude here to the right, okay? Although we might feel uncomfortable knowing that we have something of large magnitude affecting our structures. We are designing in a redundant way, okay? If our latent failure probability is significantly smaller, then maybe we shouldn't be designing with such redundancy. Or another way of putting it, if the environment of the structure is very controlled, if the possibility of things going wrong is very controlled, then we might go to the left towards isostatic structure. Maybe this is something like the design of a rocket that is tested many times, and where the space for human error in execution is very limited, okay? But still, think about what is the reliability of the space shuttles. It is certainly much more higher than the number that we get by dividing one exploded space shuttle by four or five we had, right? Over the lifetime that they had. So the reliability of the space shuttles calculated a posteriori was very low. If you consider that one of them blew up in the mission and out of 4 or 5, right? But the reliability that the number that NASA was using was certainly much higher in terms of reliability, like a 0 with many nines after it. So this goes in line with this concept. There is something missing there that could be simply a term that you add to cope with these uncertainties. And as I mentioned before, we don't need to know the exact value of this latent failure probability. Okay, in this plot, if I at least know if this value is in the last region, in the middle region, or in the left region, this would be sufficient to solve my optimization problem, considering only the objective uncertainty, only the physical uncertainty. Other questions, comments?
No?
Luis, can I ask just one more?
Sure.
Of course.
On this slide there, you're talking about topology optimization, but you're talking about discrete topology optimization, where you add or remove discrete members, right?
Yes.
And I've been thinking about the continuous topology optimization problem, where you remove elements or add elements in order to increase stiffness, for example, right? Generally. I was wondering what the structure would look like if you were able to add as objective functions something related to, probability analysis, and then to see which members appear or disappear in order to increase the redundancy of structure. Right?
They have one formulation that they use in continuous topology optimization, where they want to impose redundancy in the structure, which is they come with little defects like a square, and then they design the topology assuming that that defect could be anywhere in the structure. And then as they increase, for instance, the size of the defect, the topology changes, because it will look for alternative load paths to make sure that the structure still holds the load, even if within the presence of that defect. So it's a very similar concept, but that one is like for sure that defect will exist. And this approach here would be something like saying, or there is a probability that this hole exists. And now the optimal structure will change not just with the size of the defect, but also with the probability of it being there, right?
Yeah.
So you would obtain, for the same size of defect, for greater reliability for greater probability of the presence of that defect, you would obtain greater redundancy, or at least I think in the limit, the results that they are obtaining is what you would obtain if you assume the probability of existence of the defect equals to 1. But if that number drops towards 0, you will continuously approach the solution without considering the presence of the squares. So you actually can have a transition between the two behaviors. Yeah.
Actually, I must mention, André Labac, that one of the most important books of structural reliability was recently republished, and André Beck is one of the authors with Melkers, which was his PhD supervisor. And if I'm not wrong, André Beck is the one that wrote the last chapter, which is on optimization and structural reliability. And that's an awesome chapter, very well done job. And also, since I'm talking about books, there is another book that André Beck recently published with Elsevier that is called Conformidade Estrutural, and that's in Portuguese, of course. And it's also, for sure, it's a book that it's, for those that are interested in the topic, it's definitely worth reading it.
Excellent. Thank you, Luis.
André, thank you very much again for your participation and to again bring this topic that I find amazing on how many opportunities are open there. And yeah, I hope to see you in Campinas as well as all the other attendees in October, right?
Excellent. Thank you for your audience.
We can stop the recording.